Group webinar. My name is Mark Slutsky. I'm the Product Manager for Power and Energy Measurement Solutions here at the Ophir Photonics Group. The subject of today's webinar is, as the name says, how to choose the correct power and energy sensor using a special tool that Ophir has called the Sensor Finder, which is exactly what its name says. Just on a logistical note before we begin, I would ask that all of you with sound inputs, with microphones, please make sure that you are muted so that all participants in the webinar can get the most out of it. The total time of the webinar will be approximately 30 minutes. Questions are welcome and encouraged even. If you have any questions, please use the text chat box on the right side of your screen, and I will do my best to answer your questions either in real time or at a suitable point in the break in the flow of the information, depending on the nature and the timing of the questions. Okay, let me set up my little laser pointer here. Okay. So when we use a laser measurement instrument to measure the power or the energy of a laser beam, we need to remember that that laser beam might have as its job in life to burn holes through things, to mark, to drill, to cut through steel, who knows what. And when we're putting a sensor in the way of that beam, we're putting a sensor in harm's way. So we need to be careful that we're using a sensor that can survive the experience. And the question will then come up, how do we choose the sensor? Now, in a perfect world, if everything were nice and simple, it would be very lovely if we could have one simple measuring device that could measure everything in the world that we need to measure. Unfortunately, that kind of measuring device only exists in science fiction, for those of you who can remember that. In real life, it's usually not quite so simple. And the reason that it's not so simple is that the choice of sensor depends on a lot of different considerations. If you just take, for example, a sensor that can be used to measure the power of a 10 kilowatt industrial laser beam, chances are that that sensor won't even notice a 5 nanowatt beam, and it won't be able to measure it. On the other hand, a sensor that's delicate enough and sensitive enough to measure a nanowatt beam would get fried and vaporized if we put it into the path of a 10 kilowatt beam. And all sorts of things in between. Absorbing materials that are good for this wavelength aren't good for that wavelength, and if they're very good for measuring very high power densities, they might not be so good at measuring high average powers, etc., etc. One of the first things that we learn in any kind of engineering studies is the word trade-off. If I want more of this, it usually means I'm going to have to manage with less of something else. So because of that, in our 2012 catalog, just as an example, we have 16 different models of photodiode sensors, which we use for measuring very low average powers. We have 52 models of thermal sensors that are used for measuring average power for moderate and up on higher average powers, as well as single-shot pulse energies. Excuse me. We have 18 different models of pyroelectric sensors, which are used for measuring energy per pulse in a repetitively pulsed beam. It doesn't end there. When we need to choose a sensor, we need to consider, first of all, are we trying to measure average power, or are we trying to measure energy per pulse? What's the wavelength? Different absorbing materials behave differently at different spectral regions, and we need to take that into account as well. What's the range of power that we're expecting to have to measure, the minimum and the maximum? We need to take all of those into account. What's the beam diameter? Is the beam continuous or is it pulsed? Different solutions for measuring different kinds of beams. If it is pulse, what's the pulse width? What's the pulse rate? What's the pulse energy? It doesn't stop there. Sometimes there are additional factors. Maybe the measurement is only intermittent, meaning for a short time at a time, or maybe I need to measure a high power on a continuous basis. Maybe there are space limitations, etc. How do I choose? I think I can safely assume that most users of laser measurement instruments are not laser measurement instrument engineers. I assume that most of you on today's webinar, your expertise is in your field and maybe not so much in our field. So how do we choose? How do we choose the right sensor? And if we choose the wrong sensor, in some cases, all that'll happen is that we won't measure correctly. In other cases, we might actually damage the sensor because we chose the wrong one. Well, fortunately, luckily, happily, there is a solution. Ophir does offer a solution to help you find the solution for your measurement needs. And it's a software tool that we call the Sensor Finder. And the Sensor Finder is the subject of today's webinar. This is a software tool that's available online on our website. In a moment, I'm going to show you where it is. It can also be downloaded from our website to use offline on your computer, and I'm going to show you how to do that as well. What we're looking at here is the online version. This is a cut and paste from our web page. And I'm just going to very briefly show you what's on it, and then we're going to look at how you use it. So some of the screenshots in the webinar will be from the online version. Most of the screenshots will actually be from the offline version, very minor differences, and that's simply because it's much easier for me to do the copy-paste from the offline version into a PowerPoint slide than it is to do so from the online version, but it'll be, in most cases, invisible to you. So this is what the Sensor Finder looks like. This is just the margins from our website. It asks us a bunch of questions. The answers to those questions are pieces of information that the Sensor Finder needs to know in order to be able to narrow the choice down and recommend the right solution. So it asks us, for example, is the beam CW or pulsed? We need to answer that. Is the beam circular or I do have a mute all button, but I ask all those of you who are joining us a little bit late, please make sure that you are muted. Okay. It asks us for the beam diameter. It asks us for the wavelength. Now, of course, we need to know the beam diameter because that's the power, and the diameter need to be calculated to be able to tell the Sensor Finder what the power density is. That's one of the considerations that we need to take into account when picking a sensor. It asks us the range of power that we expect to have to measure. And then there are some additional pieces of information that are optional, which we don't have to know, but if we do input them, it'll help the Sensor Finder narrow its search down still further. Okay, just over here, I'll point out to you that at the bottom, we do also have a meter finder. The sensor is only half of the story. In addition to the sensor, you need a meter, a display, an instrument, whatever you want to call it. In some cases, it's a standalone meter. In other cases, it'll be a PC interface. Now, the meter finder, I'll just tell you now, is a little bit different than the sensor finder. The differences between sensors are important in terms of what it can do. The wrong sensor in the wrong application might not work. It might get damaged. The differences, some of you are familiar with this, between the meters are in terms of functionality. This meter has a USB interface, that one doesn't. That meter can do onboard logging, this one can't, etc., etc., etc. This one has a color screen, this one doesn't. So there it's not quite the same level of differences. So the meter finder is really just a comparison table. So we're not really going to be doing a webinar for how to use that because that's pretty self-explanatory, but there is a link from the Sensor Finder page that'll take you directly to the meter finder so that you can from there pick the right instrument to use with your sensor. There are a few other links here. At any time along the process, you can click on Contact Us to ask for any support from us etc., etc. Okay? So this is what the sensor finder looks like. And then after you've entered the information that you're entering, you would then press on the Find Sensor button, and then it'll give you a list of the sensors that meet your requirements. So now we're going to do a couple of examples. Oh, before we do the examples, I'm just going to show you how to get to the sensor finder. From the Ophir main page, www.ophiropt.com, ophiropt.com. From the main page, you see here there's links to the different divisions, the different groups. There's a direct link to the Ophir Sensor Finder. You can also get to this main page through the Newport main page, our parent company. Those of you who already work with us, chances are pretty good that you have bookmarked already the photonics group. So from the photonics group main page, this is what it looks like. Again, there is a direct link to the sensor finder. Okay, it's easy to, we make it as easy as possible to get to the sensor finder. Keep in mind all along that the purpose of the sensor finder is to make it as easy as possible for you to use an Ophir instrument to do your work. So we want to make it as easy as possible for you to find the Ophir solution that will make it as easy as possible for you to do your work. So we've kind of signposted, we've put, signs all along the various roads so that all roads will lead to the sensor finder. So let's begin with example 1. We're going to start with very simple examples and make them a little more interesting as we move along. In this case, we're talking about a CW beam, circular, and we want to measure the power of it. So picked some numbers. This is a 5mm diameter beam. The wavelength is 532 nanometers. Make sure that your units are correct, obviously. And the power range minimum to maximum. The maximum power is, of course, mandatory. By the way, if at any point after you've entered your information and you click on the Find Sensor button and you missed a piece of mandatory information, the sensor finder will hold in position there and it'll turn the missing window red and say, you forgot something. The minimum power is not mandatory. It will, the default, if you don't tell it otherwise, it'll just take as a default a minimum of half of the maximum. So if in this case I wanted to measure from 10 watts down to 1 picowatt, I would have to say so. I can already tell you that you would find no solution for that, but I digress. So in this case, I've entered those numbers. I don't need to tell it whether I want to measure power or energy per pulse, because if it's a CW beam, energy is not really relevant. So in this case, it's just a trivial thing. As a service, the sensor finder does display for us the calculated power density, just so that it's kind of a sanity check, so that I kind of know where I'm holding. Because sometimes I look at this and I say, whoa, I didn't mean that, doesn't make sense. That wasn't what I meant to say, and that might kind of bring to my attention that something's wrong with the numbers that I put in. In this case, the numbers are pretty trivial. I have nothing to enter in this example in terms of the optional additional information. So I enter these pieces of information. Okay. I should mention, by the way, that the power density is calculated very simply. Pi r squared is the area of the beam. So if I take 10 watts and divide it by pi times 0.25 centimeters squared, I get my power density. Now, you're probably thinking to yourselves, yeah, but that's only assuming that the distribution of the power through the beam is uniform. You're absolutely right. There are all kinds of safety margins that need to be built in, that are built in. This power density calculation, you're absolutely right, is assuming a uniform or top hat distribution. If you know that in your application it's very much not like that, you'll want to take that into account and take a little bit extra safety margin into consideration in the next step. So now let's look at the next step. We press on Find Sensor, and now we get a list of solutions. This was copy-pasted from the offline version. In the offline version, you need to scroll down sometimes to see the whole list. In the online version, which is what most of you will be using, that's not necessary. The whole list is displayed for you in one go. So let's have a look at what we see here. Okay, first of all, it's displaying for me the parameters of my search. Again, as a sanity check. Sometimes just that will kind of remind me, oops, I made a mistake. That wasn't what I meant to enter. And then I would say, I would click on, I don't see the button here, but there's a button that says another search. I would go back and fix it and try again. In general, the solutions are offered here in increasing order of price. It's not strictly true in all cases, but as a general rule of thumb, which means usually the first sensors on the list are probably the ones that I want to take a close look at. Percent of damage threshold. This is an extremely important column that's displayed here. This basically tells me how far away I am from the maximum. Damage threshold is that power density or energy density that creates a significant risk of damaging the sensor's absorber. The farther away I am from that, the better. In this case, the parameters that I entered are such that using the 10A thermal sensor, I'm safely very far below the maximum, so that's nice. In general, we always recommend, as a rule of thumb, to try and choose a sensor at which you're below 50% of the damage threshold. You want to try to keep away from that 50% of damage threshold, simply because even though in theory you could go all the way up to 99% and you're still okay, but as we all know, in theory there's no difference between theory and practice. In practice, that's not always true. There are tolerances, there are fluctuations. Most laser applications involve a beam profile that is not flat, top hat, uniform distribution. So in addition to the safety margins that we have built into our own specifications and into the sensor finder, we do recommend that you choose a sensor as far as possible that for this application is not going to be above 50%. In this case, we've got no problem. Another thing I'd just like to bring to your attention is this PDF column. When you click on the PDF icon of any given sensor, it will open up the catalog spec page for that sensor so that you can check out what you're choosing. Very useful feature. At any time, you can save the results of your search into a file and email it off to any of the customer support addresses that are offered to you either on the online or offline versions to ask for help. You can print it out so that you can use it for any kind of reference work afterwards. Okay, now let's move on to example number 2. Same parameters, it's still CW, it's still circular, it's still the same wavelength, 532 nanometers, it's still 10 watts, except that now I'm talking about a smaller beam diameter, 0.05. It's a 50 micron beam diameter. I take that in this example from the specifications of the laser, let's say, marking system that I'm trying to measure. I maybe don't really get disturbed too much by the 5 gazillion watts per square centimeter calculated power density that it's telling me over here. So let's say that I just enter the numbers and move along. So I click on Find Sensor and no solution. So what do? Well, the simple thing that we can do is just save, send it off to any of the support email addresses that are here and ask for help. But remember that I pointed out to you that the parameters of the search are shown to us over here as a sanity check. In this case, the sanity check will hopefully make this number jump out at us and say, wait, 50 micrometer beam diameter. Okay, that's probably referring to the size of the focal spot, the focused spot of the beam. Now, okay, in this example, let's say a laser marking system. What does a laser marking system do? Focuses a beam down so that it's small enough so that it can burn letters into maybe solid steel or something like that, which means it's zapping material. Well, if it zaps material to mark it, it might also zap material on the sensor and damage it. And if we think about it for a few more seconds, we realize that the beam needs to be focused to do its work. It doesn't need to be focused for the purpose of measuring it. So if we realize that, then all we need to do is either remove the focusing optics and measure the beam defocused, or make the measurement, do it at a location, at a different location where the beam is not focused. So in order to measure a focus, in order to measure the beam, we don't need, and we really shouldn't measure it at the focal spot location. We just find a way of increasing the beam diameter. One of the nice things about the sensor finder is it allows us to play around with these numbers, change the diameter in the sensor finder, and see what happens. And if just by changing that number, all of a sudden I get perfectly reasonable results, then I know, okay, that's what I need to do. Sometimes it helps me, sometimes it doesn't help me, but at least now I know where the limiting factor is. I might not be able to defocus the beam in my application, and then I'll need to contact Ophir and ask for some help, but that's okay. Okay, so let's move along now to example 3. In a second, you're going to see why we're calling this example 3A, actually. So now we've added another little element to make it a bit more interesting. Now it's a rectangular beam. It's still CW, but it's rectangular. So now you'll notice that I'm being asked for 2 dimensions, not 1. Okay. Different wavelength now. In this case, it's a YAG laser, and it's a 120 watt YAG beam, pretty common. 10 by 15 millimeters. It's a rectangular beam. Okay, but it is CW, so I still don't have to choose between power or energy. It can only be power. Power density is still a pretty reasonable number. There's no energy density to talk about, of course. So we press on Sensor Finder, and here's what we get. Okay, we get a whole bunch of sensors. You'll notice that these are either fan-cooled or water-cooled. For sensors to operate at 120 watts, to measure 120 watts on a continuous basis, I'm giving you a hint about what's coming. We need generally to cool them. They need some help to be able to get rid of heat at a rate of 120 watts. We could just build a heatsink, the pin fins or any of the other kind of passive types of cooling, but they would have to be pretty huge. So that's not really practical. So power sensors that have to measure these kind of power levels on a continuous basis generally are either fan-cooled, the F150A series, FL250A, etc., for FL400A, or water-cooled like the L250W, means water-cooled, or any of the others like that. Okay, and any of these are very far away from the damage threshold, nice and safe, everything is fine. But there is another little element that I'd like to bring to your attention. In many cases, these measurements don't need to be made on a continuous basis. In many cases, I need to measure the power, and then I'm finished measuring the power, and I go ahead and continue doing whatever it is that I'm doing. The measurement itself might not be on a continuous basis. It might be for a few seconds, I make one measurement, and then I'm done. 1 minute, etc. In those cases, even though the sensor needs to measure 120 watts, it doesn't have to dissipate 120 watts of heat on an ongoing basis. That actually reduces the demands on the sensor. So here, if I know that about my application, I now can make use of these optional fields to narrow the choices down further and give me a slightly more optimized set of solutions. So here I'm now telling the sensor finder, and this is why it's example 3B, same application, but I'm now adding one piece of information. The exposure time is only about a minute at a time, and then there are going to be a few minutes before I need to do another measurement. So now when I click Find Sensor, I'm getting a whole bunch of other solutions that didn't come up before, and these are not fan-cooled. These are actually, in most cases, significantly more cost-effective solutions. 5150, those of you who aren't familiar, when we have a sensor name like that, the number inside the parentheses, 150, is the power, the maximum power that the sensor can measure at all on an intermittent basis. 50, the first number, is the maximum power, 50 watts, that this sensor can measure continuously. But because we told it that the measurement is only for a minute at a time, it doesn't need to be able to dissipate 120 watts continuously, and so this sensor becomes an option, and I might have just saved myself some money and some time and some complexity. So that's another very nice feature of the Sensor Finder that allows me to optimize my search and find not just a solution, but find the best solution. Okay, now let's look at example 4a. We're now adding another component into our discussion. Now we're making the beam pulsed. Okay, so we've gone back to round just to keep things simple. It's a circular beam, 4mm diameter. It's a YAG laser, but now it's pulsed. So now I'm being asked either for the range of energies or for the range of powers. Not both at the same time. It's actually identical pieces of information. If I know the energy and the pulse repetition rate, I kind of know the power. So in this case, in this example, we're talking about 90 millijoule pulses coming in at 20 hertz. They're rather long pulses, 1 millisecond. This might be from some kind of a welding application or a medical application. Okay, and in this case, I'm interested in measuring only the average power of this repetitively pulsed beam. I might have been interested in measuring the energy per pulse. In our example, in example 4a, we're going to keep it simple. We're measuring only average power. It is important to understand the difference between these two. Okay, sometimes that does cause confusion. The power density here is no big deal, 14 watts per square centimeter, not a big deal at all. The energy density is not so trivial. It's 0.7 joules per square centimeter. Not too big a problem when we're talking about long pulses. I should mention, those of you who don't already know this, that one of the parameters that affects the ability of an absorber to withstand high energy densities is the length of the pulses. Longer pulses are easier to handle than shorter pulses. Okay, we're not going to go into why. Those of you who are not familiar with it, you can contact us offline. We can explain it. It's also explained in our catalog and on our website and previous webinars that we've done. So let's see what happens now. So in this case, we get a whole bunch of power sensors, not energy sensors, not pyroelectric, but thermal sensors for measuring power. Now, I mentioned before that this kind of rule of thumb that the sensors are presented in increasing order of price is not strictly true. It's only a rule of thumb. And here we have an example where it isn't quite holding. I'm not quite sure why it's structured the way it is, but it doesn't matter. The 10A in this case is actually farther away from the damage threshold, meaning it's a safer choice than the 3A. The 10A also happens to be cheaper than the 3A. So in this case, if I look at all the different considerations, the 10A will probably be the sensor that I would choose to make this average power measurement. The 3A is much more sensitive. It can go down to much lower powers. In our case, it wasn't such a big deal because 90 millijoules at 20 hertz is perfectly fine in terms of average power for the 10A. Now in example 4B, we're just going to change one little thing. Now, same laser, but now we're interested in measuring the energy of every pulse individually. Energy and power. We call this energy and power because when using our pyro sensors, our pyroelectric sensors, to measure the energy of every pulse, we can also measure the average power. But the reverse is not the case. So that's why we call this energy and power. Now let's see what happens. Now we're expecting to see a list of pyro sensors, and that's in fact what happens. We've got a whole bunch of different choices. Some of them involve our BF, which is the broadband absorber, which has a nice damage threshold. It can handle pretty high rep rates for a broadband absorber. And we've also got some choices that use a metallic absorber. But you'll notice that the broadband absorber on its own, it's still kind of cutting it close. It's a bit uncomfortably high in terms of the damage threshold. We're almost at 3/4 of the damage threshold. We don't like to use a sensor where the application is at 72% of the damage threshold. So if you look at some of the other cases, we'll find that some of the solutions are a pyrosensor with a diffuser. The diffuser, it's not an added accessory, it's a pyrosensor that has a built-in diffuser. The diffuser simply spreads the beam out a little bit before it reaches the absorber so that the sensor can handle much higher energy densities without getting damaged. And you can see here that the P25BF was very close to the damage threshold. The P25BF diff C, which has a diffuser, is very far from the damage threshold. It costs a little bit more than without the diff, obviously, so it's a little lower down on the list, but this would probably be the solution of choice. I should just mention that if I want the sensor to have a direct USB link to the PC on which I'm running software, and I don't need a standalone instrument on my desktop, and I don't yet have a suitable Ophir PC interface like the Juno or the Pulsar or one of those, then I might want to choose the Starlink version of the PE25BF diff C, which is this over here, where is it? Doesn't seem to be one. Okay, you get the idea. The Starlink is a family of sensors that have the direct USB link to the PC. I'm just mentioning that since it's over here, it's here kind of in our face. So in this case, we would prefer to use the diffuser-based sensor rather than take a risk of using a non-diffuser-based sensor. Okay, moving right along. Now we're adding one more component to the level of challenge of the choice. Now I'm giving it a somewhat higher energy. Instead of 90 millijoules, it's 300 millijoules. It's still the same rep rate, but higher energy. And now we're talking about a Q-switch laser, 100 nanoseconds. So the energy density has gone up. This is already a pretty high energy density. It's quite a bit above 2 joules per square centimeter. That is challenging, especially when we're talking about such short pulses. And again, now we're looking for energy and power. So what's going to happen now? We're expecting this to be a little bit challenging. So first of all, you can see that there are no solutions without at least a diffuser. So here we have a solution with a diffuser, a PE50BF diff C. It's at 60% of the damage threshold. It's a little bit uncomfortably above the 50% point. It's not the end of the world. It could probably work. If I had no other solutions available, I would pretty much be okay choosing that one. I'd be a little bit nervous, but I'd be okay. But we'll notice that there's a number of sensors that come up that include a beam splitter. We have an optional accessory. It's a beam splitter and a specially mechanical jig, and this is an added accessory. It's not a built-in. And what the beam splitter does is it reflects somewhere between 5 and 10% of the beam into the sensor, depending on the wavelength, depending on the polarization, and the rest of the beam continues through the beam splitter and keeps on going. Of course, I shouldn't need to, but I will anyways. I must mention that you've got to do something with that 90% of the beam that's continuing to pass through the beam splitter. You do have to arrange on your own for some kind of a solution for stopping and dumping that. Hopefully that solution is something other than one of your colleagues. So that's not included in our offering, obviously. But that beam splitter, it's a little bit less elegant than something like the diffuser, which is built in, but it is a solution for very many applications. It's in the catalog, it's on the website. So that was example 5. Okay, if after all that you still haven't found a solution, or if for any other reason something isn't quite working out right, you have a couple of options of how to continue. If the sensor finder found no solution, or let's say you have multiple requirements, you need a sensor that will simultaneously measure this laser and that laser, and it gets a little bit complicated. You could, of course, just do each of those as separate runs of the Sensor Finder and then compare the list of results and take the cross-section. And it's usually not that difficult. But you are perfectly free to ask for help at any time. You can click where it says contact us for further assistance. You can save your results to a file and send it to any of the support email addresses that you have. You can, of course, contact your local Ophir distributor instead of contacting us directly. They are more than happy to help you. So in general, you are not left out in the deep water by yourself. Again, the whole idea of the Sensor Finder is to make it as easy as possible for you to find an Ophir solution to make your work easier. So we will do anything we can to help you find such a solution so that you can get back to your work and use our solutions as a tool to do whatever it is that you're trying to do in your application. So in summary, the Ophir Sensor Finder is an awesome tool that does a really wonderful job of helping you find the right Ophir measurement instrument to help you get your work done. Thank you very much for being with us. If you have any questions, you have a few more seconds in which to ask them. You can, of course, ask us questions at any time offline. Contact us. Contact your local Ophir representative. On our website, if you don't know who your local representative is, on our website, you can find a list of distributors in all sorts of places around the world. Thank you very much for being with us, and have a very nice day.